All right. Uh, if you haven't checked into on campus, please do that. I know it sounds stupid that I'm giving you points for telling me what lightsaber color you are, but you are. And for anyone's record, I got orange, which is now the best color. And it also said that I'm friends with Batman. So me and Ryan Hughes are just like Batman because he got that color too. All right. Uh, so I'll give people like a minute to do that if you haven't already. And then we'll get started. All right. So today we're gonna finish content. All right. We're gonna review just a little bit first, and then we'll get on to mutually exclusive events and independent events, and then that will be it. Okay. After that, we'll talk a little bit about the final and what I'm expecting. It is already in on campus, but I'll explain a little bit about what I'm looking for, and about what the next like week or so of class is going to be without like legitimate new content. Okay. So please stay and listen to that. Also, this stuff is new and a little bit more difficult. Not difficult, just different. Um, so let's kind of get on with that. You guys didn't have any homework, so there's nothing to like ask questions about. It was really just last class was really just over permutations and combinations, and then mixing that with probability, which you see up on your screen. Okay, so remember that probability, the probability of some event happening is really just equal to the number of times our desired event can happen in red divided by the total number of outcomes possible, which is our sample space. Okay. Um, the Probably the most important thing that we can do in these problems is to find the sample space. Okay. Normally, finding the number of times our actual event can happen is slightly easier, but the sample space is probably the most important part. All right. That often has to do with the fundamental counting principle, right, which is just multiplying different numbers of ways that things can happen, or combinations or permutations, um, or just listing things. Okay, it's a lot of times it's just as easy as that. Okay, but this is what we're working with. All right, so this is the equation, which is really simple, but some of these things can get a lot harder than that. And we're going to add a little bit to that today. Okay, and the first thing I want to talk about are mutually exclusive events. Okay, so two events are considered mutually exclusive if the two events have no outcomes in common. So I'll give people a minute to write that down or read it, and then I will talk about what that actually looks like and how I would like you to start kind of thinking about probability in the near future. All right, so mutually exclusive. that just means that there's no overlap in probability. Okay, so for example, and I have these on the right, drawing an ace in a card deck or a heart in a card deck. None of those cards overlap. You are either an ace or you are a heart. There is no special card that is both. Okay, it's just ace or heart. And even like simpler example is head or tail in flipping a coin, right? Heads has no overlaps with tails. Tails has no overlaps with heads. Therefore, the probability of those things happening, those are two mutually exclusive events. Okay, and what I would like you to start thinking about probability with, and we kind of mentioned this last class, is area. Okay, so to picture this is very helpful in a lot of cases. Okay, so here we have our sample space. That's the entire box. Are we just going to pretend that the ace of hearts doesn't exist? Oh, my bad. That's not supposed to say ace. That's supposed to say like heart. Or that's supposed to say club. Spades. Spades. It's supposed to say spades. My bad. That's ace of hearts is next. All right. But anyway, to think about this in terms of area, we have our sample space, okay? And remember that the sample space is everything that can happen. And then inside that sample space, we have two different events that we want to happen. We have event A and we have event B. If they share nothing in common, then they're mutually exclusive. Okay, so again, like I said, a spades or a heart. You are either a spade or you a heart. You are either a heads or a tails. Okay, now what it looks like when these things aren't mutually exclusive is that they do overlap. So it'll look more like this instead. Okay, so these two events are not mutually exclusive because they have some overlap in probability. These are not, though. Okay, and then we're going to add on to this just a little bit. But does anyone have any questions over this so far? How many subs for a face reveal? Enough to buy me a camera. Because this computer that I have it on doesn't my actual laptop wouldn't be able to do all this. Okay. So coming up next is the probability of a union of two events. Okay, so we're gonna add a little bit of notation. That's it's not super important for the sake of this class, but if you go into anything outside of this, it's very important to know. All right, so first, let's just start with the probability of the union of two events. So a union of two events are, let's say, again, drawing an ace or a king. That is the union of two events. There are two possible things and they can be combined. All right, so the formal definition, if A and B are events in the same sample space, the probability of A or B occurring is given by the probability of A union B. Okay, so this little symbol means union. You can also say that this means or. So the probability of A or B happening is the probability of A plus the probability of B minus its intersection. Okay, so this upside down U is usually called an AND. Okay, so what does this actually mean? Again, if we start to look at this in terms of area, it makes a little bit more sense. All right, so in this sample space, in this white box, we have two events that we want to happen. We have A in red and B in blue. Okay. If they are mutually exclusive, they don't have anything in common. Okay, but if they do have something in common, well, let me back up a second. If they are mutually exclusive, they have nothing in common. And the probability of A or B happening is just the sum of those two areas. Okay. So in this case, it's just the probability of A plus the probability of B. If, though, they do intersect and they do have some outcomes in common, we're still going to take the area of those two like little ovals. But when we do that, we're actually adding this little sliver twice. So we have to subtract one of those out so we don't add an extra one of them. Okay, and I'm not sure that makes sense just right now, so I'm going to try and explain it maybe a little bit different. Okay, so in order to get the probability of these two events happening, one or the other happening, is we add this area, this red area, and then we would add this blue area. But because we're adding this area in between twice, we have to subtract one off, and that's where this comes into play. Okay, so that middle area is A and B happening. All right, so that's the union of two events. Again, like I said, though, if A and B are mutually exclusive, meaning they don't share anything in common, then the probability of A or B happening is just the probability of A plus the probability of B. Okay, this is a little bit confusing, but are there any questions over any of this on your screen? Does this kind of make sense? All right, so let's do an example, and that might make this just a little bit clearer. All right. For example, we are drawing a card from a standard 52 card deck, and we want the probability of drawing a heart or a face card. So the first thing that we need to do is to see if there's any overlap. Okay, so hearts have ace, 2, 3, 4, all the way up to 10. And then jack, queen, and king. And then there are different colored face cards. So there's obviously the jack, queen, king of hearts. Then there's spades. Clubs. And then diamonds. Okay, so we want the probability of either getting a heart or any of these face cards. So in order to do that, first thing I'm going to do is make this smaller. We have to kind of define what we're actually looking for. So we want probability of heart or face. So if we go back up to our equation, we really have the union of two events. So we need to plug in both of those probabilities. All right, so in this case, our probability of A is all of these over 52, right? So 1, 2, 3. So that would be 13 over 52, right? The probability of drawing a heart is 13 out of 52. And then our probability of drawing a face card is 12 out of 52 because there are 12 face cards. And then we need to subtract the overlap. And the overlap are these three cards, the Jack, Queen, and King of Hearts. So that's just 3 out of 52. And when we do that math, we get 22 out of 52. And that's our answer. Okay, if we look at this in terms of area, we have hearts. And then we have face cards. When we add both of those areas together, we count this little area inside twice, so we have to subtract it out. Okay. Are there questions about that? All right, and then the last thing we need to talk about are independent events. Okay, so an independent event, it means that one event has no effect, or sorry, the outcome of one event has no effect on the outcome of another. Okay, so two events are considered independent if the outcome of one has no effect on the outcome of the other. Okay, and some good examples of that are like flipping coins. Okay, so your flip of a coin on your first flip has no effect on the outcome of the second, third, fourth, fifth, and so on flips. So if you flip a heads on the first flip, that heads has no effect on your second flip, which you might flip a heads or you might flip tails, right? It's always going to be 50-50. If your two events are independent, so if A and B are independent, the probability that both A and B occur is just multiplying probabilities of A and B. Okay, and instead of writing and here, I'm going to write the upside down U. which just means and. Okay, and this is like super powerful. Like this is used a lot in dependent events. From anything from coin flips to determining like possible future outcomes of athletics and stuff like that. Like it's used a lot in gambling because usually every roll of a dice or every different hand is independent of the last. Obviously, there are a lot more like useful um, applications of that, but that's those are like the simple ones that people can really see a lot. All right. So, for example, what is the probability of flipping 10 heads in a row? Okay, so the first thing that we need to do is we need to realize that a coin flip, those events are independent, right? So if we want 10 heads in a row, we want probability of heads and heads and heads and so on 10 different times. So we need 10 different events. So really all we're doing is multiplying 1/2 by itself 10 different times. Right, where this is the first coin flip, then the second, then the third, fourth, fifth, and so on. And when we do this, we get 1 over 1024. So the probability of flipping 10 heads in a row is really just the probability of flipping a heads and then multiplying that by itself 10 different times. Okay, this should remind you of a geometric sequence because you're just multiplying by 1/2 over and over and over again. Okay, are there questions on that example? Okay, so then we'll do maybe a little bit more real of an example. Something a little bit more interesting. Okay, so for example, the Blues record on January 1st, 2019, so last year, was 15, 18, and 4. Assuming each win is independent from the next, what is the probability of them winning 11 matches in a row, 11 games in a row? This is assuming a lot. It's assuming that each win is independent, or each game is independent of the last, which is not entirely true. There's like different probabilities that go into it, but for now we're just going to assume that games are independent. Okay, so the first thing we need to do is we need to find the probability of just one win. Okay, in order to do that, we need to add up these three things. All right, so probability of winning is the sample space over how many times we actually won. So in this case, we have 15 wins, which is this number right here. And then in order to get an actual stat out of it, we just add those three numbers together and get a number. And when we do that, we get 37. Okay, so in January, the probability of us actually winning was 15 and 37. Every game, assuming independence, we had a 15 and 37 chance of winning, which is terrible, right? It's under 500. And then if we expand that to winning 11 in a row, if we assume independence, we would take this 15 over 37 and multiply it by itself 11 different times. And when we do that, we get something really small. Something like 0.0000486%. Okay. So again, like this is, it can be used in a lot of different ways. Obviously, this isn't like super important, but it is cool to think about, right? The probability of us winning 11 in a row given our record in January. And assuming independence, which obviously isn't true, right? We fired a coach, different lineup changes, whatever. But if you assume independence, this is incredible, especially then going on to win the Stanley Cup. All right. But this is how different analytics are used. Okay. If you're assuming independence of different events, which oftentimes can be assumed, and you're trying to analyze the chances of something happening, this is where it's used. Okay. So are there any questions about that example? Okay. So that is really the content, and obviously sometimes it gets a little bit trickier than this. But I want to talk a little bit about your final. Okay. So your final is actually in on campus now. It's under that probability topics, and there's really just one download in it. Okay. And that download has, I think, 11 questions, and your final will be to pick 6 of those. Okay. And some you can do right now, some you might not be able to, but that's what I want our next like week and a half to be. And I realize AP exams are coming up. Um, but if you aim to get maybe 2 of those done every class, you might have like 1 to do for homework. Okay. So that's my vision for what the rest of this class is going to look like. We're going to meet still, like I will still have an attendance prompt, but chances are we will meet in teams, and then we'll just talk about different problems that we want to do. Okay. So this isn't necessarily like a single, you have these 6 questions to do and you are only doing these. I'd like to work together on a lot of these, but that does require your attendance and your just patience and attention, right? So that's what I'm envisioning. Um, so again, that's in on campus. What I would like to do is talk about that a little bit, but let's talk about it in teams. So if you could hop off here, and then we can meet in teams for a couple of minutes and just talk about like the process of doing this and how it's going to look for the next couple of days. Okay. So let's do that. Hop off of here, get into teams, and I'll start a meeting in the next minute. Okay. So I will see you there.